Okay, cool. So next we have Yannick and Philip also from Facebook, and I'm sure that you guys are going to talk about kernel testing, and after that comes kernel rollouts, which probably require storage training. So thank you.
Cool. Yep, that's fine.
Hello everyone. So, to start, I need to take you back a few years ago. We decided to revamp our kernel strategy that we had at Facebook. We decided to go and invest really more heavily in kernel development. And the way we envision to do that is to go in what we call upstream first. The way we do it, we just write all the patches, we send them upstream with the community, and take it back into the fleet. So we started doing a lot more bug fixes, a lot more new features, and that was awesome. We had really this great kernel. So what's the next step? Putting it in actual production. So what we did, we started going around, suing each team like Federico was running, and tell them, we have this new kernel, all these new features, you should run them in your fleet, on your servers. And people were like, sure, that looks good, that sounds interesting. How did you test that? And that's where the shame started to kick in. Like, sure, it boots. We are pretty confident that you can do that. So we were a little bit taken off by this question. I'm Yannick Brosseau, this is Philip Duncan, we are both production engineer on the kernel team. I'm nations, funny. We basically deal with kernel deployment, kernel testing, monitoring, and also just debugging whatever bugs we can find in production and just have to fix it into the kernel. So to address the question that we had, we're going to go into three fronts. How do we improve building the kernel? How do we improve testing the kernel? And how do we make deployment much easier to do in our fleet? And Philip is going to start with the building part.
All right. So the way that we started out was actually first getting an internal repository that we had for a Git repository for the kernel source code. We would pull down patches from upstream or try to rebase to a specific version and then pull that into our internal repository so that we had something to work with. There were certain things that we had to make sure were available as far as like tool chains for GCC and the different tools that we would use to actually build the kernel, such as mock and RPM build. What we wanted to do is actually create a build environment that we could use consistently rather than having somebody basically running like a make command randomly on a server and then producing something that hopefully would boot on somebody else's server. We also wanted to go through and automate as much as possible all of our build instructions and how that was modeled after like the make instructions that we were trying to go through. By automating this, we took out all of the human factor from it and made a consistent build from a consistent environment that then produced a build that was close to what we were already running, which started the actual confidence level for when we were actually pushing this out to our customers. The past attempts that we had done for this is that we had first initially started with basically a bash script. This bash script, like I said, kind of got rid of all the make stuff, and somebody can go along and just give it a couple of arguments and it would produce a build. This kind of sucked. It was okay, it did produce a kernel for us, but the RPM was just on your local repository, or excuse me, on your local server. you still had to upload it somewhere. We had to go through and put it into Yum, and it didn't actually build any of like our external modules or do anything else that we would need for our libraries internally. We then moved to something kind of like BuildBot and Jenkins, and we experimented with these, and they themselves had their own issues. They didn't really have any sort of source control over the way that the pipelines could be set up. There were no ways that we can say that if somebody wanted to change the build a little bit for their purposes because they wanted, say, like a paravert option, or if they wanted like a kdump option, there was no way to easily change a single part of that script without messing up the entire pipeline. So we ended up having a lot of, flakiness with this project, and it was difficult to continue moving forward with it. Eventually we decided that we should probably kind of scrap these and kind of go back and look at what we were trying to do, because the kernel itself is a very difficult thing for us to build and get everything related to the kernel built and then pushing out to our environment in an automated fashion. So what we did was we stepped back and looked at automating every single aspect of this. Like I said before, we wanted everything to be as cookie cutter as humanly possible. We wanted every single kernel to look exactly the same as the previous one, except for the diff changes that we were specifically pulling in. And so we really wanted to take advantage of like all of the SRE type of automation tools and like the tasks that we were trying to look at. So what we did was we turned to our existing infrastructure. Our existing infrastructure is what we use for building all of our web tools and all of our internal basically all of our internal code tools for our backend services and for our web services as well. We have an entire team that would be dedicated to supporting this, and the only problem was that it wasn't really built for something like building the kernel. What we had to do is go through and find every section of the existing build infrastructure, see what was kind of missing and how it was kind of close, figure out which part would work best for us, and then extend it to meet our needs. This ended up being a lot less work, not only in the short run and actually getting something set up and running, especially in our production environment where everything's already kind of locked down for security reasons and we can't exactly just throw a random open source project in there and start messing with it, but also just from the aspect of, from ongoing support, having support from that team when something does fail or break down, or if we're trying to get something to, if things start to backlog, we can actually go to that team and figure out what's going on. So we started with the actual build process and getting something built into a container. And there were a few things that were a little bit off, and there were some configuration management stuff that we had to fix. Once we had the build, we were able to then take those RPMs, expand them into that same container, and then build all of our external modules and get those out of the way as well. Once that was done, we were able to take the built artifacts from that, all the external modules, all the RPMs from the kernel, upload it to our shared storage that was just described to you guys, and then use that to distribute it across the fleet. It ended up being a very cool system because we can basically automate almost every aspect of this. This let us have basically hourly builds. Every diff that we put up, we are able to build a new kernel for. Every hour we do a build just to see if everything is still working and make sure that our entire system is working. And it kind of monitors itself by just the fact of if things are building correctly, we'll see it in the build process and through the testing process as well. It also turned it completely automated by a time series event rather than us having to go and at all manually run a build. The only time that we now run builds is if we want to run one for testing and we want to run it off a specific branch, or if we're doing official release builds and we want to make sure that it's a specific branch that we're cutting off of. Once we had the builds into a central storage place, we needed to then start going through with testing. The first question for testing was, does it boot? This is a very simple sounding question, and a lot of people will use things like VMs to be able to answer that type of question, but it's a very important question as well because we're trying to make sure that when we give a new kernel to any sort of service owner, that when we tell them that it's a short maintenance window, that it would just be a quick reboot and their stuff will come back, that's actually true. So why is this kind of a hard problem? So when you look at how you install a new kernel on a host, you're changing the boot parameters, you're changing how things go through, and you're hoping that it comes back from that boot. There are ways to kind of fake it, and there's also ways of getting around the full reboot, such as kexec. But those ways don't really work, or they're not really indicative of our actual production environment. So the reason I say that is that you could use VMs, but we don't really run VMs in our production environment. So if we have any sort of hardware failures, or if there's any sort of driver issues, or if there's anything with the bootloader or anything, we would never actually see that. The other option would be using something like kexec in order to skip the whole reboot process itself, but there are again still some driver issues and some aspects of that that aren't fully fleshed out, and it's a little bit buggy, so we didn't want to have to rely on that as a production service. So what we wanted to do is do this as often as we do a build. So for every single build that we do through either continuous or hourly builds, we'll throw it on a few servers and see, does it boot? Is there any issues with this? We do this both for the continuous and hourly builds and all of our official builds as well, just to make sure that everything is kind of covered the same way. We also pull in a version of an upstream branch and build that locally and kind of see what's coming down the pipeline to see if there's any changes that could break either our build system or our test system along the way. So before we actually rebase anything from upstream into our internal repository, we've already kind of been running it and building it, and we at least have an idea if it's going to break. So the type of test that we wanted to run, there's many different testing frameworks out there for the kernel, between Autotest, LTP, Avocado now, XFS tests, Trinity Fuzz tests. And with all of these different frameworks available, it was tough for us to really make a decision on which one we wanted to go with, or if we even had to make a decision in the first place. What we ended up deciding to do was just support multiple frameworks. So this way it allowed all of the kernel developers or the community at large to basically submit tests to us. We could then use those tests and test as much as we want. The only thing that we had to do was basically collect stats and collect results for each one of those tests. The way that we did this was we standardized a little framework around these frameworks that would run the test however it needed to for that particular framework type, collect the results back, and then just standardize it into a JSON form that we could then parse later into our standard test format. This worked great because it let us basically use a simple CLI to push things into our normal test infrastructure, which was again the same thing that we used for all of our web code and all of our normal internal tool builds. This gave us a baseline for health for every single build that we did, so that we had some idea of whether or not, when we push this out further to all of our customers, if that build is healthy and whether or not we would have any issues with it down the line. The main problem that we currently still kind of have is actually related to performance testing. This is because performance testing for the kernel is extremely difficult to actually interpret. We can run the tests, but knowing what those tests mean and whether or not there's actually a gain in performance or a loss in performance, or if we have an increase in reliability or a decrease in reliability for that cost in performance, is very, very hard. We can say that there's, say, these performance changes that occur, but does a 1% change occur because other processes are happening, or if there's something exactly with the kernel that's causing it? So because of this, we still have kind of limited performance testing, but we're working on getting that as better so that we can have something to at least have a baseline off of. Currently, the systems that we have under test are everything from network to file systems, syscalls, and cgroups, and even for our containers and the BPF testing, since we use BPF relatively heavily. We want to get more in from the community, and we're trying to get as many tests as possible so that we can move forward with additional testing and contribute back as much as possible. Part of the problem with this many different types of tests and systems that we're trying to test is that test health isn't necessarily extremely obvious. It's hard to tell if it's a configuration change or something that we were doing on our side, if it was that the test was even designed to run in an environment like ours, or if it's actually a broken test. So when things do start to fail, we have to go through and determine if what changed, what was wrong with that part of the kernel, if there was anything that did change, if it was a broken test that needed to be updated, and if we did update it, do we then just disable it because maybe it doesn't work in our environment, or do we send those changes upstream? These are all kind of complicated questions that we're trying to work towards fixing, and for the most part we do try to send things upstream whenever possible, and we try to enable as many as possible that make sense for our environment. Next we're talking about kernel deployment, and Yannick will take care of that part.
So once we have this testing, building automation in place, we have this more confidence in the kernel, but we need to get it to the fleet. The first question we have to overcome, though, is, do I really want the kernel? So as we get into to people, and the first question is when we see people, why do I want that? When we develop the features, we see all the nice thing there, but a lot of people will come to you and it's been running fine for years. Why do I want to upgrade? So we need to push harder, the new feature, the new performance, make sure we have really good metrics about what's improved into the kernel, and sometimes we find out this is going to give you a few % improvement in the performance or in the throughput, or you just have this really great tracing tool to debug your problem in your fleet. So you should probably use this latest kernel that we give you. It also fixes a lot of the latent problem. You maybe never seen a kernel problem because you never hit it with your current workload, but if you change anything at some point, you might hit a bug that is there for forever in the kernel, but it actually fixed into the next kernel. So the first stage of deployment, and it's kind of just an hybrid between testing and deployment, is to do some canary. So that's when we finish an official build and get ready, pass all the testing, we send it to a portion of the fleet. So the first way to do canary, we pick a small portion of each services. It can be 1%, couple of hundred machine, or even just 3 machines, depending on the service. And we just put it there, let it bake for a week, 2 weeks, just to see if there's any problem there. The other way that we do canary is actually go and install the kernel on 2 sets of machines. The first set will get the new kernel, the second set will get the old kernel, and we just either replay the same traffic to both machines, or replay the same command, the same request, and see how they behave. And we can easily compare if one is better than the other, because we know that they are doing the exact same thing. The next step is to actually go to the whole fleet. The way we do it and the cadence that we do it is every week we build a new release candidate with all the latest change that we have. We do that up to 4 to 6 times. So 4 to 6 weeks we release a new official kernel. So that's the cadence that we get push the new kernel into the fleet. Every month and a half, people will see a new kernel in their own machine. Every year, we take this kernel and we rebase on the new upstream kernel. For the last year, we've been working on the 4.0 kernel, and we're currently working on the 4.6 and starting the release candidate process. So this kernel has been released upstream about 2 months ago, so we're already getting ready to deploy it in the fleet because we want to benefit from all the latest changes that we can have. So the first step is rebooting the machine. As obvious it can seem, for some services it's a really hard question. You would need to take account, like Federico mentioned, how do you drain the machine? Do you drain the machine? Can you do you have the capacity to take some loss into your service? And more importantly, does your service come back properly after being rebooted? That's a lot of questions that you need to make sure you have in your fleet before you can actually do and deal with the reboot process. The next big consideration is to go slow. It's probably a really good practice for any software development, deployment that you do. You don't want to put it in all your fleet at once and just figure out if there's a big problem there. It's even more important with the kernel deployment because it takes a while for the bugs to show up sometimes. Sometimes you get, you boot, you get a crash right away, it's really easy. We're gonna fix that, roll a new kernel. But sometimes it can takes a week. You might need to wait for your peak traffic, your peak request time to actually trigger some issue in the kernel. You might have a combination between some maintenance software running while your production traffic is running to actually trigger the condition that will create a problem in the kernel. So the way we do it, it's like an extension of the canary process. When we get ready to release the official kernel, the final kernel, we put it in the same canary system, the 1%, the 5%, and we just go and add more machine as we go there in the fleet. The next consideration is there's no unique way to deploy the kernel. It would be easy to think, I'm going to develop one system, one way to push the kernel for all the whole fleet. It's all the same, similar machine. We run all the same OS. It should be easy. We tried that. We failed. We decided, okay, let's use this system. It's going to be perfect for everybody. Turns out it's not true. Some system will have different draining characteristic, and it will work. Some system will work really well. If you have some stateless machine that can just take any reboot anytime, and you just set a rate limit, it's fine, but you get into some more complex situation. So basically we have 4 ways to upgrade the kernel currently in our fleet that we use. The first one, really simple one, we have a system that just scan a set of machines that are registered in the system and just check if they are running the desired kernel. And we can compare that, and if it's not the desired kernel, just raise an alarm, and our auto-remediation system will just pick it up and do the remediation on the system by just installing the kernel and rebooting the machine. The next approach that we have is really similar, but it's more like systematic approach. You actually pick, as a human, the set of machine you want to operate with. And you just said, okay, let's go, let's reboot those part of the service, this cluster, and it will just go and you specify a specific concurrency, a specific failure rate, and it will just go through all the machine 1 by 1 or 10 by 10, depending on your setting, and upgrade the kernel there. The next thing that we see now a lot, especially with the bigger services that have to deal with a lot of machines that have way more complex rule to deal with. They might have to run pre-checks on the capacity or the drain logic. Can I actually drain 10 machine, or can I drain 100 machine? Or do I need to check if I have enough replica before taking down this machine? So these services will have implemented these part of the logic, and they will run the tools that they have at the specific rate by using some of the common component that we have in the fleet to develop this specific service-specific script. And the last method we do is actually to go and just use our configuration manager system, and we use Chef to actually go and pre-install whatever latest kernel it is, and just let it there, and just wait for some of the event to reboot the machine. You might be running a bad kernel that is okay, but just keep crashing once in a while. So we just put the latest kernel and just wait for the kernel panic or other bad situation that might happen. If you enable out of memory panics, you might get into this situation that will just get your machine to reboot. So we're gonna just put them there, or if you do any other maintenance, it will get the latest kernel at that point. So that's a way to get your kernel upgrade without disrupting any other service. With that situation, we might need at some point to use any of the other method, but at least we benefit from whatever event happen to get these good kernel. One thing with all these methods is actually to have one unique way to choose which kernel you want in your fleet. Instead of having 3 different configuration systems, we use this one source of truth that is used for the kernel upgrade, but also the provisioning process, the repair process. So whenever a machine goes through all this process for your service, you know you're always going to get the kernel you selected for your system. So one of the main takeaway here, it's kind of obvious, SREcon, we talk a lot about automation, but you want to automate the most out of that. And it's even more important because if you have this kernel upgrade process and you need to upgrade thousands of machines, it might take a while to go through it. So you start your process, and let's say it takes a week to do. It goes through there, you bunch a cluster, you know you need to start it again for the next cluster, but then you forgot to actually trigger it, and then you only think about it a week after. It happens to me a couple of times when I had to do this manually. So you kind of lost the full week if you forgot to do it manually. So you want to make sure you automate everything there, make sure you go to pick the next set of kernel, or just set it up so you actually rely on our deployment system and just link it to our testing and deployment, and just whatever there's a new kernel available, the automation will just pick it up and you don't have to worry. One thing too that some people worry about is they're going to see some of their machine taking down. If they're not aware that the kernel upgrade process is a thing that's happened in the fleet and they're rebooting the fleet that are completely normal, people not aware of that will oh, something happens, my machine rebooted, and get into panic mode and try to debug everything. So people need to be aware that this is a thing, and after a while people get used to looking at the graph like this small and continuous wave into service being up and down, that is a normal thing. It's something okay, and you need to have this like capability to distinguish between a normal reboot and a bad reboot. With all of that, monitoring is key. With all that, to make sure that whatever runs right now is good, or whatever we deploy is still good. So we have two main tools that we use for monitoring on the kernel side. First, we use kernel Kdump with basically whatever kernel panic occurs. We would collect all the core dump, all the memory, and the current call stack that happens that trigger the panic. We collect that, put that into a dashboard so we can see all the panics happen, and we can see trendings on either panics. Do we get more panics as we release new kernel? Do we get less panic? The second thing we have is we use the network console, where basically we send all the kernel message to a server, and we log that. And with that, we can generate alarms about warnings, about panics, about alternative situation. And again, we can see trending. We have dashboard per kernel, we have dashboard per service, so we can see, oh, does the kernel affect a specific service or a specific version? And we can distinguish that easily. We implemented a net console daemon. It's open source. It's on a GitHub FBK util. If you want to deploy that into your fleet, it's really efficient to collect all the logs from all the server and do whatever computation we want with that. One last thing to think about. You might deploy the kernel. It's all fine. You build your RPM. It's really fun to use. But there's some components that are tied to the kernel that you might also need to deploy and keep up to date. I'm thinking about each tool, IP route, MC logger, some of the perf, like the perf tool might need to be used, XFS tool, all the file system tooling. You might need a beta tool to not really work, because the old tool usually work with the new kernel for backward compatibility. But if you want to use all the new features that are available in the kernel, you will need new tooling in your fleet. So you need to tie that. You might not need to upgrade your whole OS, but there's some specific tooling that needs some upgrade. So as a summary of all the things we did to be able to respond to the question like how do we do things properly in the kernel side. So on the building side, we improved the process to be consistent and easy so that everybody on our team can generate a build, and it's going to be always the same if we point to a specific hash in the tree or specific tag. On the testing side, we added a lot of tests to increase confidence into the build, so we know when we release a new build that is actually working for different workload. And lastly, on the deployment side, we automated the most that we can, and we're still working on doing more automation. And we go slow. We slowly deploy and gain confidence as we go to more and more machines in the fleet. With all of that, the current state of the fleet, the majority of our system is on 4.0 right now. We still have a few, also the kernel that we've been working on the last year. There's still a few machines on 3.10, but the upgrade process is going well. And as you see, there's a really small slice that's already running 4.6 in production in our fleet. Not shown there, we still have a few 3.2 machines that are some systems that are really harder to upgrade, and we're still working on automation and with those teams to make it happen and make sure we can go to like the latest kernel in their fleet. Lastly, as Philip mentioned, the one thing that is actually the main thing that we want to add is like adding more tests. There's a lot of coverage missing. There's another talk after the break talking about kernel fusing and testing. So there's a big need for more testing. We're gonna add more, we're gonna write more tests. We plan on sharing as much as we can. But if you have any tests that can test some component of the kernel, please share them with the community. There's many places where we can put them. It's always a little bit confusing. Do we use them the kernel self-test? Do we use the LTP? Do we use other framework? But I think the main idea, one of the big discussion we have right now in the kernel community is like, how do we improve testing and how do we collect all those tests? So if you have any specific workload tests that you can share, please come talk to us. If you don't know what to do with them, we're gonna find a place for them. And we're gonna just continue building on more automation. Thank you. Probably have a few minutes for questions.
Hello. one of the most frustrating things about systems work is hitting a bug, doing a lot of research, finding somebody else already hit it, fixed it, it's upstream, and you're deploying. So the patching element of what you're doing sounds interesting to me. And you've developed this whole framework for doing it. Do you look at libc or OpenSSL or Java VMs? Do you could take your approach and change wherever you've written kernel to something else. Are you going to take over the world for patching?
So the way our work is mostly focused on the kernel, and as well, I would wish to see more of that happening in some other project. And we already see it in Facebook. Some other teams actually taking this upstream first approach in some of the project, and especially on the infrastructure side, if we see any problem that we can fix, we usually contribute it back, because it doesn't make sense to just keep it for us, and it's just make it harder when we rebase to the next version to take it back and have to patch it again. And then often one of the issues we had on the kernel side, we just like forgot some patches and rolled the kernels like, oh, that was required for one of the surveys. So we are more active on the kernel side. I cannot really speak for all the other teams at Facebook, but definitely we are looking at doing more open source stuff there.
Hello, so let's say that you do the canary and everything is fine, then you start rolling out, and at some point you realize actually there is a bug that you didn't catch during canary. How sophisticated is your rollback automation at that point? Have you ever needed to do like full or semi-full rollback?
Yeah, we try the most as we can as never roll back and always roll forward, so fix it and go forward. It might happen some really critical bug, and we're just going to reuse the same automation that we have for deployment to just set the previous kernel into the tooling and just let it roll the new kernel. We always have the possibility to go manually and just install the kernel everywhere and just reboot the machine if we really need to. But we always try, that's why we do the canary process and make sure we monitor everything so we catch all these bugs. And usually at that point, if there's 10% of machines, the service is probably still fine even with the bug, so we can probably live for another week with it, especially if it's there for like 3 weeks or like already a year with the same bug. We can probably live with it, just fix the patch and roll it part of the next week release.
Back when I was doing the kernel testing qualification stuff, the biggest pain in the ass for me was, someone's introduced a new log message in the kernel, and in some weird situations it'll log 100 gigabytes a day into disk. Built tests for that, and that was great, but I was wondering, could you share any war stories about really hard to find bugs that required arcane and weird tests to make sure they wouldn't reoccur?
Yeah, there's many, I'll say zero. Huh? I did zero. I don't know this one. I don't know the Cardup one. I'll do the Cardup, you can do the other one. So we had a small issue. It's not as arcane maybe to say, but somebody in between 4.0 and 4.6 changed the way Cardup happens, and for user application, and we just released it and released the kernel, and after a while some people start complaining like, I don't have any like core dump on my system, all the core dump are corrupted. And we're like, okay, what is it, and what do we do? So we had to go back and write some testing there to actually implement like, okay, can we do the core dump? That was core dump to a pipe, and we have to implement like a testing around that to make sure it doesn't happen again. So that's one small example, like kind of arcane, like a small subsystem, that's something that is easy to test, but there was no testing upstream or anywhere else about this specific feature. We still need to contribute the test for that, but that's something that we need to add. I don't know if you have any.
One example that I know of is that there was an issue where on our build environment, because we use the same build environment for all of our other builds inside of Facebook, they had a bunch of packages that they were expanding and just getting rid of over and over again and kind of reusing different containers and temp directories. And one of the attempts to remove one of these just completely failed installed, and it was starting to go and like actually affect multiple machines at a time. We were seeing this bug come up over and over again. What ended up happening was that there was a bug where basically all of the user space tools wouldn't see a specific inode because the inode was actually 0. And that was actually a valid inode number that you can pull in like in most of the file systems. So we had to go through and patch all of that, and now we try to make a test to basically see, can we create an inode 0, and if we can create it, can we delete it properly and everything and go forward with that. But because of the fact that we use the build environment as well, and that particular stuff is stuff we're trying to get rid of and make the build environment more stable for them as well, they're actually one of the ones that want to work with us the most, and they're very easy for us to convince to upload or upgrade things and work with us. So when we do patch things like that and find stuff that's just broken in the build environment, we can usually just kind of patch that first, roll out the newest kernel to that very, very quickly, and kind of use that as also as like a test bed to see like how are things working for everything for us.
No more question? Thank you.
Thank you.